Hello everyone, welcome to our talk from adoption to innovation, LinkedIn SPIRE journey. I'm Junyuan from LinkedIn's security infrastructure team.
I'm Wei, also from the LinkedIn security infrastructure team. Today we are very happy to share our journey with the SPIRE, from where we started, how we adopted in the LinkedIn on-prem, and some challenges and how we address the challenges, and also the lessons learned. It's a multi-year effort in the LinkedIn, but it's really important that it has been a very important part of our infrastructure. Let's start with a bit of context, why we want to change. LinkedIn runs their own data center with a broad microservice. Most of them need the identity in the format of X509 certificate, so that all the communication, all the requests can be authenticated. This relied on the internal PKI system for years. The internal PKI system was a handwritten server, very basic Python server without the intention of scale. It doesn't have the standard identity format, so it's very hard to integrate with the new systems. It also doesn't have the rotation or tracking, making the management very hard. That's when we start exploring other options, which is SPIFFE and SPIRE. For people how many of you are using the SPIFFE or SPIRE? Yeah, cool. Yeah, for people who haven't used that, they are a pair of the open source project. SPIFFE is a set of open source standard, which is defined how to issue identity to the workload or other identity types. The core concept is a SVID, which is SPIFFE verifiable identity document in either 509 X509 certificate or JWT token. Inside of the SVID, it contains the SPIFFE URI in the format of trust domain identity path. SPIRE is a very popular and well-adopted SPIFFE implementation. It consists of SPIRE server and SPIRE agent. The SPIRE server is a central authority that manages and signing identities. SPIRE agents run on the node level. It's connect to the SPIRE server, maintain the connection, perform attestation, and making certificate request. And also it caches the certificate request for the workloads. So SPIRE also is an API-centric framework, and also support various plugins. It makes the SPIRE a very perfect choice for all cases, for reasons such as foundational. Because LinkedIn runs their own data center, so it needs a solution which has very minimal dependencies. We cannot use some cloud-native solution. We cannot use some in-cluster solution. That's why SPIRE is the foundation of the SPIRE, making it very suitable. Also, the SPIRE is very scalable and highly available. Its internal design, such as distributed caching and certificate caching logic, making it able to handle large large number of nodes and large number of identities. And also, SPIRE is very extensible. It can easily integrate with other plugins, such as attestation plugin, and also with other on-prem integrations. And finally, SPIRE has a strong community support. It's continuously updated and maintained by the community. Let's take a closer look at how we adopted LinkedIn, starting with the trust model. In all deployment, each environment has its own trust domain, such as production and staging. And each trust domain has a corresponding signing CA chain, and it has a name constraint defined for that. So the URI name constraint ensures that the issued certificate is only valid for the associated trust domain. And also that's also explain why we define the trust domain as prod.ly, basically from the child domain on the left side to the parent domain on the right side. And we also define the internal SPIFFE identity standard, such as we have a workload and we have users. And we also have additional information, such as location information embedded in the X509 certificates. We didn't use the token issued by the SPIRE because we have our own internal token server, and that's also be updated to follow the SPIFE standard we defined. The standard we defined is not just for the SPIRE or other identity, it's also very important for the authentication authorization implementation in the company, even the logins. So notably, we have to update the internal authentication authorization libraries and policies to integrate with the new SPIFE and perform access control. Let's see the overall diagram. This is the overall diagram. We deploy the SPIRE server in a regional cluster, for example, in the production data center 1 versus production data center 2. So every regional cluster is an independent deployment. It uses the HSM inside the data center for the signing CA secrets. In the server side, in addition to the main, on the server host, in addition to the main server process, it also runs the combination of the standard and the custom plugins and other controllers. On the node side, SPIRE agent runs on the node as a systemd service. The node has SC Linux enabled to protect the SPIRE agent and other process on the host. When the TPM device is available for the node, SPIRE agent will also leverage the TPM for the node attestation. To achieve the high availability and scalability, we have 5 server instances per server group with a load and the user agent using the client-side load balancing when connecting the server. This setup supports up to 50K nodes per cluster in our practice. And finally, we also integrate with the internal logging and the metric system, which is eventually integrated with the Microsoft Azure Data Explorer that enable a very convenient query and monitoring. So we do have some key challenges in adoption, such as how to build the trust and how we manage the dynamically entries to issue identities, and what if when running SPIRE agent isn't always applicable. And my teammate Junyuan will walk through the challenges and design.
Thank you. Let's talk about how to approach the first challenges, building the trust. We will start with the SPIRE server CA bootstrap to ensure the workload identities can be verified and issued. We deploy SPIRE server in the critical host with extra security protection, such as full machine isolation. This feature only allows the SPIRE server and the service it launched can run on the node. On startup, the SPIRE server will use the TPM store pin to authenticate with HSM and get a signing CA. After that, it will use the signing CA to sign and issue the leave certificates for the workloads. We evaluate different options to store the signing CA, including HSM and TPM. However, both options will introduce additional overhead for leave certificate signing. Therefore, we chose the SPIRE in-memory CA signing to meet our performance requirements. After security bootstrap the SPIRE server CA, we want to ensure the node connected to it are trusted. And that's where the TPM-based node attestation comes in. For people unfamiliar with TPM, you can consider TPM as the lockbox, which proves a node is trusted. It includes the authenticities and integrities. Authenticity refers to what the node is, and integrities means what state the node is in. The root of trust of TPM is endorsement key, which is a unique factory embedded key. This key including 2 parts, public and private key. So only the public is extractable. TPM-based node attestation will use a TPM to verify the nodes are trusted and grant access to those nodes. Usually, the trust chain to prove the node is authentic starts with the vendor certificate, which validate the EK, and the EK is used to prove the TPM is authentic. And finally, the TPM in turn attests the node. The trust chain can verify the TPM is authentic. However, it's not able to prove the TPM or node is managed by one organization, such as LinkedIn. Suppose attacker who can control the authentic PTM can actually pass the trust chain verification and eventually break the TPM-based node attestation. One of the approaches we use is to identify the nodes that's matched by linking and then register the node EKs to the database to establish the root of the trust chain. For this purpose, we integrate with standard data center provision workflow, which records the device physical location in assets database, including switch, port, side cabinet of the node. All of the operations are complete before the first power on of the nodes. Without the database change, compromising the location information will require the attacker to have physical access to the data center. After that, we identify the nodes matched by linking according to the recorded location, and finally, we register the TPM EK public key for the matched node. Let's dive into the detail about TPM EK registration workflow. So when the node starts for the first time, the Bootstrap OS that we trust starts before the regular OS. It will interrogate the TPM to get the EK public key and calculate its hash. After that, it will query the system to get the series number and location information and send all of them to the build system, which will verify the location information against the access database. Once there's a match, it will save the EK public hash into the EK database. With the EK public hash registered in the database, our TPM-based node attestation works as shown in the diagram. In high level, this workflow is built on top of a TPM, SPIRE agent, and SPIRE server. It uses the registered EK to ensure the remote TPM and node is matched by linking. Also, ensure the EK private key is securely protected inside TPM, and that is the node authenticity. After that, based on the fact that EK private key is securely stored inside TPM, we certify the SPIRE agent private key is also inside TPM. And finally, we use the certificate signing request signature to ensure the issued certificate is bound to the SPIRE agent. So up to this point, we have verified the node is authentic and also is managed by linking. In the future, we will integrate with Mirrorboot to ensure the node's bootstrap integrity. We have established the initial trust through the TPM-based node attestation. Now, on top of this trust, let's talk about how to approach the second challenges, that is identity assurance. Alive is the SPIRE design. In order to issue a workload identities, 2 steps are required. The first step is workload registration. It actually defines which workload can receive the particular identities in registration entries. For automation, we develop controllers to monitor different API events and then update the entry dynamically. The second step is called workload attestation. In particular, the SPIRE agent collects workload properties such as UID, systemd ID, and match those information against registration entries. If there's a match, the related identity will be issued to workload. At Linkins, we leverage open source SPIRE plugins, for example, systemd, Unix, to cover most of our use case. For the workloads out of the standard attestation, we develop core stack-based attestation to balance the security and flexibility. Here are some examples we supported for the workload attestation. Let's walk through one example about Kubernetes TLS bootstrapping across the entire fleet at LinkedIn. When the SPIRE server starts, it will bring up the entry controller in the same node. This controller watches cluster manage API for different objects, such as node objects. It will update the registration entry database through the SPIRE server API over Unix domain socket. The SPIRE agent, on the other hand, periodically synchronizes the entries to the local cache, and the configuration agent performs workload attestation against the SPIRE agent based on UID. Once it will delegate the serve file fetching and rotation for the kubelet. So far, we have talked about how to extend existing SPIRE architecture to solve a key problem. However, there are some use cases at LinkedIn where the SPIRE agent-based architecture is not the best fit. First of all, in firm workloads that request a large number of short-lived certificates, will introduce a lot of overhead for dynamic workload registration. And since the certificate are short-lived, we don't need all of the security benefits from the SPIRE agent, such as identity rotation. Second, workloads run in cloud environments, which is secure by the provider, such as Azure. So agent-based node attestation is not necessary. For some environment, we have limited or no access to the underlying infrastructure. Agent management is challenging. And finally, some workloads run in non-Linux environment, such as macOS. In this case, agent deployment will introduce additional complexities across different platforms. So at LinkedIn, we implemented an agentless architecture, which removed the SPIRE agent and entry registration workflow. At the same time, we introduced an intermediate gRPC service between the client and SPIRE server. This service will handle request authentication and also talk to the SPIRE server API over Unix domain socket or UDS. The workload, on the other hand, will use one-way TLS connection to talk to the gRPC service directly instead of the SPIRE agent. Right? So let's walk through GitHub Action use case to better understand how it works. When the SPIRE server starts, it brings up the gRPC service in the same node. This service will request its own identities to the local gRPC call means X509 SVID through the SPIRE server API over UDS. The client or workloads, such as GitHub Actions, also wants to get its own certificates for different purposes. For example, image signing and security fetching. Basically, it sends a custom means request to the gRPC service. This request including GitHub OIDs token as the authentication method and means X509 SVID request, which defined by open source SPIRE. Once the service receives the request, it will validate the OIDs token against GitHub OIDs provider and ensure the token claims match to the certificate signing request attribute. Once that match, it will make the same local gRPC call to the SPIRE server API to get the workload certificate and finally forward back to the client. Hopefully, this gives you an overall idea about how we approach different challenges. Next, I will hand over back to Wei to talk about the key lessons we learned from our journey.
Yeah, so a few key lessons learned along the way. First is stay flexible. SPIRE is very flexible, and we rely on the plugin system to handle the different scenarios, such as TPM and non-TPM cases. Not all the hosts in LinkedIn have the TPM device, so we developed multiple types of plugin to handle that. Other than the plugin, the SPIRE's own API centric system, making it is very powerful. And we using that to develop other components for needs, and also as well for when developing the agentless mode. Second, issuing certificate is only the beginning, and switching from other type of certificates to the SPIFE is actually changing the authentication method. So that's why you need to plan all the related changes and roll out thoroughly. Third is the availability. And we have invested the availability early and build the metrics into all the components. And in practice, that has been very useful in troubleshooting some issues. And also, achieving the early alignment with other teams is essential. The success of the SPIRE coming from that being the part of the broader infrastructure rather than on its own. Thank you for joining talk today, and we are happy to get any feedback and stay connected. And now we are ready to take any questions. Yeah, please.
You mentioned that one of the challenges is after the identity is established, how do you authorize it properly? What is your process for governing the authorization policies? How are they reviewed? And how do you know that your authorization policies sufficiently address all of the risks that this process is introduced?
You mean the authorization after, such as when we are workload getting the certificates, or in authorization in the identity assurance?
For example, how do you decide who gets to register? There must be policies in there, authorization policies that are important, that are critical for trust.
Yes.
So how do you govern what those policies are? I imagine they're changing a lot. And so how do you know that they're properly reviewed and that you've actually addressed the risk that you've introduced by allowing this new capability?
Yeah. So for example, when we are creating the entries, for example, in all the server side, in addition to server address, the server process, we have the own additional controller. All these additional components are using the libraries, authorization libraries, that internal Golang app we use. So you treat that additional controller as a standard kind of gRPC server. So for example, who can call the controller, how the controller are integrating with other LinkedIn backend service, they are performed as a standard kind of microservice. And all the components are interacting with the SPIRE server only through the Unix socket domain. So the request was not always directly go through the SPIRE server API, but rather than go through this additional controllers that is developed internally.
But from a business perspective, who reviews and approves, and how do you get visibility so that this can be reviewed by security? Or is it just the programmers who know who can review it?
I think in terms of availability, all the entry creation and the register certificate generation are still generating all the logins and events, and this data are still unified. So we can talk more about that part. Any other questions?
Next question.
Do you encounter any performance issues, specifically the large latency when a workload first fetches credentials, like for the first time?
Yes, yeah, we do encounter that. And even when we initially started, we also set up a very large sync up interval, like 30 seconds. That makes the latency is very relatively long. We later changed to that 15 seconds. But in the practice, we observed that the first time fetching, the taking could be 30 seconds or 1 minute. So we have worked with all the integration parts to make sure they are aware of this limitation, and they are waiting for the certificate to be available for the first time usage. So that step, that latency, that lagging was still existing.
Yeah, the first time when we sync the entries from the SPIRE server to the SPIRE agent, at the latency like 30 seconds. Yeah.
That's also in some cases in agentless mode, and that latency is much shorter because all the requests were handled in the one request, no agent involved. Yeah. Okay.
Hey guys, thanks for the talk. Is SPIRE and SPIFFE just positioned for non-human identity, or can it also be positioned for human identity?
Good question. I think the SPIFFE standard, the name suggests it's for everyone, but basically SPIRE has been mostly focusing on the workload, which is service. But SPIFFE standard doesn't have to, and in our case, we have our own user token endpoints, and we also issue the format with a SPIFFE format. So yeah, I think it's just your design choice. Yeah, I think for the overall backend, because we want to have a very uniform, consistent authorization library and interpretation. So that's why I decided for our user token endpoint, it also follows standard as we just shared.